Okay, we're not going to be able to finish this lecture, but we can start it. And this is the first kind of, let's say, sophisticated volume visualization technique that we're going to talk about in this module. It's a non-trivial technique, and it's the most complicated topic that we have talked about, or we will talk about in this module so far. I would say everything up to now has been pretty straightforward, but this starts to get a little bit more difficult and a little bit less straightforward and a little bit harder to understand. So we're going to talk about marching cubes, and before we talk about marching cubes, which is a 3D version of a surface extraction algorithm, we'll talk about marching squares, which is a 2D version. But we won't be able to finish it today, we'll just be able to start it. But before we do, we're going to discuss some terminology. The first term is called an isosurface, a surface representing a constant valued scalar function. That the VTK stands for the Visualization Toolkit, which is a very popular volume visualization book. Now, what does that mean, a surface representing a constant valued scalar function? An isosurface is a surface that has a special property, and the property is that every value on that surface is the same, or a constant value. So if you can imagine a CT scan or an MRI scan, every data sample that corresponds to, for example, skin will have the same value, the same scalar value. So the skin will correspond to a constant scalar value, and it will show up. We can represent these constant scalar valued subsets of the data with a surface. And it's just like in the conceptual visualization, volume visualization pipeline. Remember the first example we went over with the images of the body? There was a surface representing the skin. There was another surface representing the bones. And there were surfaces representing the soft tissue. Well, each one of those surfaces had a constant value, a constant scalar value. And that's what an isosurface is. Don't worry if it doesn't click immediately the very first time you hear some of these terms. Sometimes they'll click later on. I still remember hearing the term for the first time and not understanding it. Yeah, but if you do have questions about the terms, then just let me know at any time. An ISO value, the scalar value used to generate an isosurface, also from the VTK. ISO means one, right? Everybody probably remembers that from their, their Latin classes or something. In this case, why would an isosurface be called an isosurface? It's because there's only one scalar value represented by the surface. It's a unit scalar value. And it's classified as an indirect volume visualization technique, and they're extracted from 3D volume data. Does this remind anybody of anything that you might have heard before? What's the next slide? Okay, there it is. I should have shown the next slide. But these are examples of isosurfaces. So the data on the surface of the skin is all the same. It's all the same scalar value. And the data along the surface of the bones is all the same scalar value. And same with the soft tissue and other soft tissue. It looks like 4 surfaces there. Everybody knows what a surface is, or has maybe not the formal definition, but you've seen surfaces before, like, I don't know, a balloon, or the surfaces on the other slide. And but you've never heard the term isosurface before, probably. Has anybody ever heard that term before already? That would be surprising. But you have heard another term that's similar to that term already. That's not 3D. But have you ever seen curves of constant scalar value? Anybody ever? Well, it's a trick question. Does anybody recognize where they've seen curves of constant scalar value? This is about surfaces of constant scalar value. But maybe you've seen curves of constant scalar value somewhere. Or edges or lines. You all have, actually. I have psychic powers, and I know that you've all seen curves and edges and lines of constant scalar value, but you've never heard them described that way. So a curve of constant scalar value means a curve that has the same value everywhere along its geometry. And you've seen those, you see those you've seen them in a few different places. One place you see those is on the weather report. When you watch the weather report, you see the UK divided up into different regions of constant, anything? Constant, anybody? Like, everybody here watches the weather report. They've seen it hundreds, maybe thousands of times. Actually, it's not very educational, is it? You've seen it thousands of times, but you don't know what you're looking at. Constant temperature. So you see, when you look at the weather report, you see curves or lines of constant temperature. Like the region surrounded by this curve, all is 15 degrees Celsius. You see that when you look at the weather report sometimes. You also see curves of constant pressure on the weather report sometimes. So you see like the UK, and you see these curves that look like clouds, right, in there, placed around the UK. Those are curves of constant scalar value. So you've seen those, you've seen them millions of times. Anybody know what they're called? Those curves of...
Isobones?
That's almost very close to correct. Isocontours. So you've seen isocontours millions of times in your life already. That's the magic word. You've seen them on the weather report. Anybody else know where you've seen them, but not as often?
Topological maps.
Yes, topological maps. And what do they represent on those maps?
Elevation.
Exactly, curves of constant elevation. So that's an isocontour. Does everybody think they can understand what an isocontour is? Like those curves of constant scalar value on the weather report and on a map? Because that would help. If you can understand those, then what I should do is really have an image of some isocontours on the slide. Next time you look at the weather report, notice the curves that you see in the weather report. Those are isocontours, curves of constant temperature or pressure, or maybe something else. It doesn't have to be those two things, but usually it's temperature or pressure. It's usually pressure. But we're extending that idea now to 3D. So instead of a curve, it's a surface of constant scalar value. Everybody confused now, hopefully? So these are some more. Oh, here's an isocontour. Here is an isocontour. Now, does it start to look familiar? Can you imagine the map of the UK with different bands of temperature and pressure now in the weather report? Each of these curves represents an isocontour, or a constant valued scalar function. These are isosurfaces. This is a slice, by the way. That's not an isosurface, so it's a slice and an isosurface. There's one isosurface for the skin and another isosurface for the bone. So they're an indirect representation or an indirect volume visualization technique. They're also object order. Well, the Marching Cubes algorithm that we're going to talk about. And they depend on somebody like the user, usually an expert user, because this is usually specialized, choosing the right ISO value. An expert user will know, I know that skin corresponds to this ISO value. I know that bone corresponds to this ISO value. So they will be looking for very specific ISO values. And ISO values separate different boundaries. They're essentially boundaries between different substances in reality, in practice. So your skin is a boundary, isn't it, between the outside world and whatever, your physical body. And there's an isosurface or an ISO value that corresponds to your skin. And then the bone has also a boundary, doesn't it? The outside of the bone. And that also corresponds to an ISO value. And then all of your soft tissues have boundaries as well. And that's what medicine is, the study of those boundaries, essentially. That's kind of what life is, actually, the study of boundaries. So ISO values and isosurfaces represent boundaries, and boundaries are the most interesting subsets of volume data, period. They're very interesting. You're usually not interested in uniform space. You're interested in the boundaries, right? You might not be interested so much in the space occupied by this room, but you're interested in the exits and entrances and the chairs that you sit on and the floor and the ceiling and so on, the boundaries or the surfaces. And we're going to talk about how to extract those. And here's a preview. Before we talk about the isosurfaces, we can talk about isocontours, planar data and isocontours. This is an isocontour right here, drawn through a two-dimensional data set. And I'm going to draw one part of that, the upper left rectangle, if I can draw it correctly. 5, 6. It's nicer to draw it with a marker, actually. Well, I'll just leave off that part. So the question is, how can you compute the isocontour? The input is data on a 2D slice for the 2D case and the 1D isocontour case. We're going to move up to the 3D case where the data is presented on a three-dimensional grid. But before we do that, we're going to have a preview at the 2D version. So if we have this 2D planar data set, how do we actually compute the isocontour? And in this case, the isocontour is, the ISO value is what in this case? The user has chosen an isocontour corresponding to the value of what in this case? 4, correct. So the user says, show me the isocontour that corresponds to 4. I want to see a curve, and everywhere on that curve corresponds to the value of 4. And this is the way the algorithm works. The algorithm traverses each square one by one. So this is one square for each square. I'm going to erase that question mark. And then there's another loop for each edge. And each edge in the square. So this square has 4 edges. I should probably say like in the square, right? For each edge, test is the ISO value. Is ISO value along edge? So along edge. I could write that a lot better. Now, what does that mean? Is it along the edge? So we're testing, in this case, we're testing the value of 4. Here we're looking at this edge first, and we know that 4 is below 5, but above 3. So it is actually in between here somewhere. So in this case, it's true. Is the ISO value along the edge? If it's true, we know we have an intersection. So intersection equals 2, and then compute point. This is the intersection point. So the value of 4 occurs between the value of 3 and 5. And we can use interpolation to compute that the intersection point is here, 4. Right, if it was 3.5, the intersection point would be a little bit higher. If it was 3.1, it would be a little bit higher. So that would be, we compute the point there. This is the true case. If this is the false case, else we just do skip edge, and then we can make some comments. No intersection. So if we go to the next edge, right, this is for each edge. This should be indented by one. And 4 each edge. So we did this edge. What about this one? The value of 4 is higher than 3. It's here, it's also higher than 3. So there is the ISO value along this edge? No. Like there's no value of 4 between these 2 points. So it's in this, we can enter this case. We skip the edge. We don't compute any points. No intersections. Skip. What about the next one? We'll go to this one. It doesn't really matter the order. Here, 4 is above 3 and below 6, so we do find it. Is the ISO value along the edge? Yes. The answer is yes. And we'll use interpolation to approximate the position there, right? So 4. And that's that case. And then what about this edge? So we're doing for each square and then for each edge. 4 is below 5, and it's also below 6. So is the ISO value along the edge? The answer is false in this case, so we skip the edge. And that's the end of each edge, for each edge. And then the next 4 is connect intersection points. Like that. So that's I connected the question. What's your name?
Joe.
Joe.
Yeah. So if say they were searching for 3, as obviously that edge has, like the entire edge is 3, would that then intersect every point along the line or intersect with the line?
That's a good question. Do you see this? This is the statement here, separates values greater than f0 and below f0. That statement corresponds to, like, is the value along the edge? So you have to make some sort of a decision, like, is it greater than 3 or less than or equal to 3, for example? If you chose the less than or equal to 3 case, then it would intersect 3 and 3. However, you would not. What you'd want to do generally, though, is you would just skip this edge, because really you're looking for an intersection case. You're looking for a case where one value is above the ISO value, and another value is below the ISO value. So in fact, you'd end up skipping it if you chose 3. You want 2 data samples that are on both sides of the ISO value, not exactly on it. So you'd end up skipping it. That's a good question, by the way. Did that make sense? That is a summary of the ISO contours algorithm. For each square, for each edge, test each edge for an intersection. If the intersection is true, compute the intersection point. Really, this should say compute intersection point. And then it's connect the intersection points, and then at the end it's end for each square. I should make this a little bit better. For each square, and then for each edge. For example, I should draw an edge like that. Yeah. And that's it. Like that's the summary of the marching squares algorithm. And so we processed one square at bionic speeds. And then we move on to the next square and run the same set of tests. We march through the squares one by one, performing those tests. And we just repeat over and over again. So you can see here from this diagram, okay, there's an intersection, there's an intersection. There are no intersections along here. There's an intersection, there are no more. So wherever you see that ISO contour, you have a value that's below and above on both sides of the ISO contour. And then you generate the you compute the intersection points. Whenever you find that edge case, you just compute the intersection points, and you end up with an isocontour. Yeah. Did that make sense? Hopefully. And what you'll notice is that you have separated this area, this plane, into two regions. That's the result, and it forms a boundary. So this region is the boundary or the area with all the data samples above 4. And on the other side of the boundary is all of the data samples below 4. So you've separated that plane into two regions now. And you've created a boundary between the two regions, the boundary of 4. Now that's an academic example because the 4 is, we don't know what it represents, but it does, in a real data set, that 4 would represent some property of the data or the object being studied. Marching squares. Any questions about marching squares? I guess we will stop there because, yeah, we're out of time. It was so exciting. I felt like it's hard to stop, actually. I can see everybody leaning forward in their chairs like, oh, keep going. If you want to see what's next, last year's lecture is still on YouTube. Like, you can have a preview if you can't wait to see what's coming. Can I just